All right, let's look at three more examples of Gaussian elimination with back substitution. This first system, we want to solve that. So we'll first rewrite it as an augmented matrix. That's going to be 2, 5, 1, then 3, negative 4, 16. All right, we want to get a 0 here. Now this one, since we've got a 2 and a 3 there, there's not really a great way of doing that. You could do row 2 minus 3/2 of row 1. And there's nothing wrong with that. But here's what I want to do. Instead of doing that, why don't we subtract row 1 from row 2? That way it'll give us something with a 1 there, and then we can subtract a multiple of that off, and we won't get any fractions. So let's do that. We're going to do row 2 minus row 1. So we get 2, 5, 1, and then 3 minus 2 is 1. Negative 4 minus 5 is negative 9. And 16 minus 1 is 15. Now let's swap the two rows. So I'm going to do row 1 swap with row 2. So we get 1, negative 9, 15. And then 2, 5, 1. And now I can do row 2 minus twice row 1. All right, so that's going to be 2 minus 2. It's going to be 5 minus 2 times negative 9. So that's 5 plus 18 is 23. And then we do row 2. So 1 minus 2 times 15 gives me let's see, 1 minus 2 times 15, that gives me negative 29. Yeah, negative 29. Yeah. All right. So that gives us this. And the numbers aren't very nice here, but we can solve it. This bottom row gives us 23y equals negative 29. So y is negative 29 over 23. And we'll plug back in on top to get x. X gives us, let's see, we get x minus 9y equals 15. So x minus 9 times negative 29 over 23 equals 15. So x is 15. Let's see, that together this is positive, so we'll subtract it. 9 times 29 over 23. Now, that is exactly the type of problem that a calculator is made for. 15 minus 9 times 29 over 23. 84 over 23. I'll be honest, I made this problem up intending it to have a nice solution, but it didn't. So anyway, that's how we can solve that using Gaussian elimination with back substitution. Let's look at this next one. First up, but before we do it, let's look at it and see if we can figure out how many solutions it has. Are these two lines parallel? Let's see. The top one, if we take the top one and multiply by 3/4 and change the sign, that would give us negative 6. If we do negative 12 times negative 3/4, that gives us positive 9. So it's either parallel or they're the same line. But if we do 16 times negative 3/4, we don't get 6. So that means these are parallel, and that means there's no solution. But pretend we didn't know that. What would happen if we tried to use Gaussian elimination with back substitution? something neat is going to happen here that's going to also tell us this has no solution. Let's first write it as 8, -12, 16, then -6, 9, 6. All right, we're supposed to get a 0 down here. But here's what I want to do first. Since the top row is all multiples of 4 and the bottom row is all multiples of 3, let's divide by 3 and 4. So I'm going to do row 1 divided by 4 and row 2 divided by 3. That's going to give me, let's see, 2, -3, 4. And on bottom, it's going to give me -2, 3, 2. So my next row operation would be, in order to get a 0 here, I want to do row 2 plus row 1. So I get 0 here, 0 here, and 6 here. Now think about what this bottom row says. This bottom row, if we rewrite it as an equation, it says 0x plus 0y equals 6. Or more compactly, just 0 equals 6. Obviously that's false. So if you take this back a step, well, first off, whenever you get something like this that says 0 equals some number that's not 0, that immediately tells you no solution. Another way to think of that is, this is saying, which values of x and y make this equation here true? And the answer is no values of x and y. So by doing this sort of row operations, we went from something that's, maybe not obvious that there's no solution to something that is obvious. All right, let's do one more. This last thing, solve this system. X plus y equals 10, 2x minus y equals 2, and x minus y equals -2. That's 3 lines, and if this system has a solution, it means all 3 of them go through a point. So I've already graphed that on Desmos here, and we can see that all 3 lines do go through a single point. So this does have a solution. If we were feeling lazy, we could just look at it over here and say the solution is 4, 6. Maybe that's not lazy. Maybe it's doing it the most efficient way. But whatever. Let's look at what happens if we do this with Gaussian elimination and back substitution. Yep. Let's see. We get 1, 1, 10, 2, -1, 2, and then 1, -1, -2. All right, what should we do here? Well, we need to get a 0 in both of these spots. So I'm going to do row 2 minus twice row 1. I'm going to do row 3 minus row 1. I don't have much space, so I hope this doesn't take many more steps. So let's see. Row 3 is easier. 1 minus 1 is 0. -1 minus 1 is -2. And then -2 minus 10 is -12. All right. Let's see that middle row. It's going to be 2 minus 2 is 0. Then -1, I'll tell you what, I'm going to write this out. -1 minus 2 times 1, that's -3. And the last one, -2 minus 2 times 2, that gives me -2 minus 4 is -6. Oh, I made a mistake. You might be yelling at the screen right now. Yeah, this one right here, this is a really easy thing to do. What I'm doing here is row 2 minus twice row 1. I just grabbed my numbers from the wrong places. So I'm doing this minus twice that. So that's going to be 2 minus 2 times 10. So what is that? 2 minus 20 is negative 18. All right. So my triangle, I'm trying to get a triangle of zeros down here. Really, this is the place I need a 0. Notice these last two rows really tell me the same thing. The bottom row tells me that negative 2 times y is negative 12. And the middle row says negative 3 times y is negative 18. So both of those tell me that y is 6. So once I've got that, I can back substitute it in to the top. The top says x plus y is 10, so x is 4. And that matches what we saw a minute ago on Desmos. All right, so just getting things into triangular form, that's what we're sort of playing around with right now. And this is arguably not quite triangular form. But there is a more systematic way of doing this, and that involves putting matrices into reduced row echelon form. But we're going to save that for next week.